Imagine a world that did not exist in the past prior to time itself. On the edge of the universe, a huge mass of matter is waiting to generate the energy that powers everything we see today. But is this really the start? We have been told for years by physicists that the Big Bang, an explosive event, was the beginning of everything. Nevertheless, recent revelations suggest that this might not be the case. What would happen if the world were caught in a never-ending cycle with beginnings and endings? It is a mystery that requires us to delve deeply and reevaluate everything we believe to be true about the world. The Big Bang Theory has been a reliable explanation for how the universe started for decades. Atoms, molecules, stars, and galaxies as we know them were created by a massive explosion of matter, according to this model. This theory provides a consistent explanation for the universe's creation and is the foundation of our understanding of it. However, more recent research has begun to challenge this long-held viewpoint, suggesting that the universe's beginnings may be a subset of a much more extensive cyclical process. The Big Bang Theory has been questioned by physicists like Brian Cox, who argued that the concept of something emerging from nothing is fundamentally flawed. The idea that the universe might not have a single origin but rather be part of an infinite cycle of expansion and contraction in a never-ending cosmic dance has added an intriguing new dimension to the discussion. New insights from the James Webb Space Telescope contradict the idea that the Big Bang was the absolute beginning of the universe, adding to this debate. Scientists have rethought the fundamental question, if the Big Bang wasn't the beginning, then what was? As a result of these findings, this question pushes our understanding to its limits and delves into the mysteries surrounding the Big Bang Theory. We now know more about how the universe started thanks to the Big Bang Theory. This model predicts that approximately 13.8 billion years ago, the universe was smaller, hotter, and denser than it is today. All of our universe's elements were formed in a matter of minutes at that time. The size of a peach and the temperature of the universe, including the stars and galaxies, were once the same. From the abundance of light matter to the electromagnetic radiation left behind by the early universe, this narrative is consistent with current observations. The Big Bang Theory, on the other hand, is only part of the story. A thorough comprehension of the world's earliest moments is missing. The limitations of our current physical concepts are the source of this difficulty. Particle physics and general relativity form an excellent theoretical framework, but when looking at the earliest moments of the universe, the mathematical complexity becomes enormous. The singularity, a region of infinite density at the beginning of the universe, is one characteristic of this complexity. It seems almost absurd to propose that the universe was compressed into a very small and dense form. To meet this challenge, physicists must investigate new physics frontiers and devise strategies to circumvent these constraints in order to gain a deeper comprehension of the universe's past. String theory comes into play at this point. As a physical model that can combine forces with other fundamental forces, particularly the strongest force, string theory is proposed. It suggests that a new framework that goes beyond the limitations of our current theories can provide an explanation for the universe's past. The word eon, which means year and end in Greek, is used in string theory. According to this theory, the Big Bang as we know it was the result of a historical event rather than an actual beginning. It suggests that the world is a component of an ongoing process that spans both the present and the future. In recent years, a lot of attention has been paid to the string theory-supported idea of a cyclic universe. String theory provides a solid mathematical foundation for the concept of a universe oscillating between expansion and collapse, which has been under consideration for a number of thousands of years. The universe operates in cycles, with each cycle characterized by expansion, evolution, collapse, and yet another major explosion. Roger Penrose, a well-known physicist who won the Nobel Prize for his contributions to our comprehension of the universe, is credited with developing this concept of cyclic cosmology. Penrose was fascinated by the mathematical relationship between the future universe, which was cold, vast, and devoid of matter, and the early universe, which was characterized by extreme density, heat, and smallness. Penrose insisted that when pushed to their absolute limits, the two conditions should be equal. According to Penrose's theory, the absence of matter is the driving force behind the creation of everything we see in the universe, which may seem counterintuitive. Black holes consume the entire universe before eventually evaporating into scattered photons, resulting in the Big Bang, according to this perspective. The world emerges from nothing, an empty world, in this great uncertainty. How to describe a world that appears to be either dense and warm or cold and empty, depending on perspective, is the key. A complicated mathematical method called proportional transformation, a geometric transformation that alters an object's size while maintaining its shape, is essential to this comprehension. Penrose demonstrated that this arrangement can connect the cold empty state and the hot dense state, organizing their spatial structure despite their disparity in size. Penrose, on the other hand, suggests that these extreme circumstances render the concept of time meaningless. The universe moves from an old cold state to a young hot state in a linear fashion. The hot, stuffy feeling comes from the cold, empty past, but this problem doesn't happen over and over again. Size and time lose meaning in these extreme circumstances, and the cold, empty, and hot, dense states exist in distinct registers. From the observer's perspective, there will always be nothing but a bleak, empty existence. In the universe, physics and philosophy are deeply intertwined. In addition to providing theoretical explanations for where these changes came from, this theory also raises deeper philosophical concerns. Even though recent advancements in the field lend credence to Penrose's ideas, a deeper question remains. Where does physical reality originate? What brought about these alterations? One of the central metaphysical issues is what constitutes something other than nothing, and this enables us to consider it. There are three physical factors that are connected to the origin of these changes. First, there might not be a physical reason. Second, there may be an infinite series of cycles, with each cycle representing a distinct world and each world's first major form determined by the world that came before it. In a universe that repeats itself, a single cycle may occur, with the beginning of the cycle being explained by some aspect of the cycle's conclusion. These concepts are very appealing because they provide more complex definitions within a physical framework and eliminate the need for arbitrary events. Quantum mechanics influenced Penrose's description of the concept of a series of infinite cycles. According to quantum mechanics, a physical system can be observed in multiple states at once before settling into a single state. Penrose proposed that transitions between cycles are brought about by random variable events that affect each cycle. Because it demonstrates the capability to detect subtle artifacts or anomalies in the remaining radiation, this concept presents experimental physicists with a number of exciting opportunities. One of the primary goals of human curiosity and scientific research since the Big Bang has been to comprehend the universe's origin and nature. Humans have always sought to unravel the mysteries of the universe, whether through ancient philosophical writings or contemporary cosmological theories. The study of the universe's beginnings has led to profound discoveries and fascinating theoretical frameworks that challenge our understanding of time, space, and substance in astrophysics and contemporary astronomy. For physicists and cosmologists, one of the most intriguing questions is what the universe was like before the Big Bang. Although the Big Bang theory offers a convincing explanation for the universe's transformation from a hot, dense state to its current expansive form, it does not answer the question of what, if anything, preceded this cosmic event. The idea that there was a time before the Big Bang has profound philosophical and scientific implications, which push the boundaries of what we know and understand. To answer this question, a number of theoretical paradigms have been proposed, each of which provides distinct insights and perspectives on the early universe. The multiverse is one such idea, which holds that there is a vast collection of universes, each with its own set of fundamental constants and physical properties. Our universe is just one of many universes in the multiverse framework. Each universe has its own set of physical laws and came from different starting points. Some interpretations of quantum mechanics and the theory of the expansion of the universe give rise to the concept of a multiverse. Global inflation holds that the early universe's rapid expansion of spacetime may have resulted in the formation of pocket universes within a larger multiverse, each with distinct characteristics resulting from random quantum fluctuations during inflation.